In this video, we'll be solving the equation 11 cosine squared x plus 7 sine x cosine x equals 6 for x being between negative pi and 0. First, I'm going to subtract 6 from both sides. And one thing you notice is this equation has both cosine and sine. Ideally, we would want to have one of them. Or if I can replace this and have one variable, let's say this whole equation depending on only y, without any trig functions. So that's actually what we're going to do. So first we're going to let y equal sine of x. And we know that sine is opposite over hypotenuse. So we're just going to treat the y as y over 1. So if I make a right triangle with angle x, the opposite side is y, the hypotenuse side is 1. Pythagorean theorem says this missing side is the square root of negative y squared plus 1. Now cosine of x becomes adjacent over hypotenuse, which is why we get the square root of negative y squared plus 1. And so now we can replace sine and cosine and only have y. But the problem here is that we have a square root, so what we have to do is square both sides. But before we do that, we want to isolate the square root. So we're going to move the 5 minus 11y squared to the right. And then we can square. So squaring the square root, that will go away. And then we have 7y squared becomes 49y squared. And then we square the 11y squared minus 5 to get this. Okay, now we have to distribute this 49y squared to both the negative y squared and 1. And at the next step, we're going to subtract, or rather move these terms to the left. So we'll end up with negative 170y to the fourth plus 159y squared minus 25 equals 0. At this point, if you want, you can factor, but having a fourth degree polynomial is a little intimidating. So if you want, you can transform this into a quadratic by letting z equal y squared. So then z squared becomes y to the fourth. And so you have negative 170z squared plus 159z minus 25 equals 0. This is the quadratic we want. We can factor. So I can pull out the negative. And now, if I want to solve for z, I would just set the 5z minus 1 equal to 0 and the 34z minus 25 equal to 0. This negative here, I don't really care because I could just multiply it to the other side as negative 1. So when I set both factors equal to 0, I get z is 1/5 and 25 over 34. Now, my original equation depended on x, not z. So what I have to do is work backwards. We said z was y squared. So y squared is 1/5 and 25 over 34. But y we said was sine of x. So replace y squared with sine squared. I want to get x eventually, so let's take the square root of both sides. And taking the square root of both sides, you want to make sure you have the plus and the minus. So the positive and the negative. And now to solve for x, you have to apply the inverse sign to both sides. Now, technically, you should have a 2 pi times a integer. So this is for all solutions of this form. But we're missing one other solution, or rather one other set of solutions. So let's just take this for example. Let's say we have this y value, or this point right here. Let's say this is a solution. We'll call this theta. We know that for sine, the second quadrant also has the same value here. This also would have to be theta. Now, if I were to draw the circle, let's say, this whole thing right here, this top half is pi. So if this is theta, that means this angle right here has to be pi minus theta, okay. Which is what we have to apply here. We do pi minus the angle. The angle is the inverse sine, whatever that angle is. So we do pi minus the inverse sine for both of these. And I'm just going to include the 2 pi n1 and 2. Although technically you could say, you could call this n3 and n4 if you want. Okay, but remember, we have to have x between negative pi and 0. So we may need to play around with these n's so that we fall in that range. Okay. So now what I do is I calculate the inverse sine of each one of these. So the 1 over root 5, negative 1 over root 5, plus or minus 5 over root 34. So when I do this, I want to make sure I'm between negative pi and 0. So like this one and this one works. Now for the ones that don't work, if let's say 0.464, if I subtract by 2 pi, that will still not be in the interval. Same thing with 1.03. So I can't do anything with those. And for those that are in the interval, if I add 2 pi or subtract 2 pi, it would take me out. Okay, now we look at pi minus the inverse sine. So we'll do pi minus inverse sine 1 over root 5. That's 2.678. If I subtract by 2 pi, I'm still not between negative pi and 0. So this is not going to work. Now pi minus inverse sine of 5 over root 34. That's 2.111. Subtract by 2 pi, I'm still not in the interval. Now pi minus inverse sine of negative 5 over root 34. That's 4.172. But if I subtract by 2 pi, I am in the interval. So just by looking at these, I only have 3 candidates for x. So those are negative 2.111, negative 1.03, and negative 0.464. Now the common mistake here is to say, okay, these are the final answers. But because we did all these substitutions, you want to make sure these work. So always plug it in to the original equation. So for us, it's 11 cosine squared x plus 7 sine x times cosine x equals 6. And when you do that, you only see that negative 2.111 and negative 0.464 work. So those are the only solutions.